Welcome everybody to the next installment of the SHIELD webinar. Today we are doing something new. We are starting a mini series within the SHIELD webinar that we called it Young Voices. And the reason we wanted to give a chance and a platform for the young researchers coming up in our field to talk about their research and giving them also an opportunity to talk about their background, where they come from, and then switch to the research. So I have the immense pleasure to have these two wonderful researchers that I know for some time. Elena Povornikova and Parisa Mustafavi. Both of them come to us from APL, from Johns Hopkins Applied Physics Lab. So let me just highlight some of the interesting facts about both of them. Elena is now a space scientist in the space exploration sector of APL. And she served as a heliophysics science lead in the Interstellar Probe concept study. She's also deputy PI for SELA mission or Sheila mission and associate investigator for the PUNCH mission. She got already in her young career several awards. She got the Air Force YIP award, and she also got the very prestigious NASA Living with a Star Jack Eddy postdoc fellowship while she was at the NRL. She did her PhD. Some of her research was with me at the Boston University, and she was also advised by Vladislav Izmodeno from Moscow University. So we're very excited to hear about her research that she will talk next. Parisa is a postdoc fellow at the Johns Hopkins Applied Physics Lab. She did her PhD with Gary Zank at University of Alabama. Can I ask whoever does not have their sound mute to mute themselves? I can hear some echoes in the background. And she did her study, her MS and her BS in Tehran, in Shahid Beheshati, if I pronounced it correctly. Parisa, you can forgive me.
That's right, yeah.
And she already was in one of the webinars in SHIELD talking about her trajectory. So we welcome her back. She also got an incredible award, the Fred Scarf Award for her PhD. And she did, and before coming to APL, she was in the Princeton University working with Dave McComas. So before we start, I just want to share my screen really quickly. Usually what I do at the beginning of every webinar is just to explain what SHIELD is about. So I will just go really quick. SHIELD is one of the drive centers that were funded for phase 1 from NASA. We are very hopeful to get phase 2. We will be applying at the end of this year for an extension for 5 years to a full-fledged center. The idea of SHIELD is to develop a predictive global model of the heliosphere. And we are combining both MHD, particle physics, localized small simulations, kinetic physics, and of course, observations to develop this model. So we have a pretty large team. You can visit our website here down below to see what SHIELD is about. And the main drive behind it, why is interesting to study, not just because we are interested in heliospheric physics, but we also were interested in understanding habitability. And our heliosphere and it's one example that we know of a habitable astrosphere. There might be other out there, but we haven't found yet. So we need to understand ours first before we can understand what makes an astrosphere habitable. We do know from our astrosphere that we shield a lot of galactic cosmic rays. This is one of the goals we would like to understand. This is our website. So go dive into this website. There is lots of interesting stuff there. In particular for outreach, we have lots of amazing videos, testimonials. We are working on putting them together in a kind of a video summarizing all these amazing testimonials we got. If you're interested to make a testimonial, why you came to space physics, what are your challenges, what are opportunities you had, please contact us. You can email at shieldoutreach@bu.edu or my email. Okay, so at the end of the webinar, we are going to put in the chat a survey. We are using those surveys kind of to gauge how these webinars are effective and also kind of help us plan future ones. And our future one that is coming up next month is from our own Heather Elliott. She's coming back to us to give a talk about, she gave a talk, how to write a good proposal and a good paper. Now she's coming back of talking how to create an effective scientific presentation. And this was very popular. She gave our first webinar, so she's coming back with more tips. So please tune in. Next, it's our webinars, it's always the second Friday of every month, 2 p.m. Okay, so I'm going to stop blabbing. And I think I'm going to give the floor to Parisa first, right?
Yeah, thank you.
And so you can share your screen. Hello, John.
Okay. Okay, now you can see my screen.
And just 1 second, Parisa, before we start, just an organizational tip. At the end of the webinar, we are going to get questions for both of them. So we're going to go to Parisa, hold your questions. You can put it in the chat, but we are going to first hear Parisa, then Elena, and then we're going to open for questions. Okay, go ahead, Parisa, sorry.
All right. No, thank you so much, Mera, for inviting me again to give a talk at your webinars. Okay, today I want to talk about the heliospheric shocks propagating beyond the heliosphere, and we want to know how far does the sun's influence extend into the interstellar medium. Okay, so this is the outline of my talk. First, I'll give a brief introduction about the heliosphere, and then I'll talk about our model and how we model some of the shock, for example, heliospheric termination shocks, shocks in the inner heliosheath, and very local interstellar medium shocks. And then I'll talk about some of the open questions that we have about these shocks in the heliosphere and interstellar medium. Okay, forgive me if you know all this. So our sun travels in the galaxy with the speed of about 25 kilometers per second. And then so it emits lots of energetic particles and solar wind into the heliosphere. And they go very fast, faster than sound speed. So they have they move very fast and until they reach the termination shock. When they reach the termination shock, they heat up and slows down, and then becomes subsonic. And the boundary where the pressure of the heliosphere become equal to the interstellar medium is called the heliopause. And this medium between the termination shock and heliopause is inner heliosheath. So here is the interstellar medium, and here is the very local interstellar medium is the region that is affected by the heliosphere. And there might be a bow shock or bow wave in front of the heliopause. Okay, so here is the map of the heliosphere and interstellar medium in the logarithmic scale. Now let me talk about some of the missions that studied the outer heliosphere. Voyager 1 and Voyager 2 were launched over 40 years ago, and they were planned to be planetary missions. And fortunately, they got extended and became accidental interstellar mission. And now they both are interstellar medium and making measurements of the in situ measurement of the interstellar medium for the first time. And here we have New Horizon. It was a mission to study Pluto, and then it began also started to go out of the Pluto to the termination shock. And unfortunately, it will run out of the power before reaching the termination shock. There is IBEX here at 1 AU, and it is mapping the global interaction of the heliosphere with the interstellar medium by measuring the energetic neutral atom. All right, okay, so interstellar neutral atom can enter the heliosphere without any problem because they are neutrals. They enter the heliosphere, then they can have charge exchange with the solar wind. And when they charge exchange, they become charged particle, they start gyrating around the magnetic field. So then they get picked up by the solar wind. So that's why they are called pickup ions. Pickup ions are very important, especially in the outer heliosphere. You can see here from New Horizons observation. This is from McComas et al. 2017, where they look at the pressure. Here, they have plotted the pressure as a function of distance. And so here 1 AU is Earth, and here's the termination shock. And they have plotted the pickup ion pressure in red. This is thermal gas pressure, and green is the magnetic pressure. Since New Horizons doesn't have the magnetometer, they're using the magnetic field from Voyager data. So you can see that after about 20 AU, pickup ion pressure becomes the dominant pressure, larger than magnetic pressure and thermal gas pressure. So we can see that pickup ions are very important in the outer heliosphere, so we should include these particles in our models. In Zhang et al. 2014, we have calculated the collisional timescale between pickup ions and thermal gas, and we saw that in 3 regions, supersonic solar wind beyond 10 AU, inner heliosheet, and the very local interstellar medium, collisional timescale is greater than characteristic flow time of the region. So pickup ions are not equilibrated with the background, and we should treat them as a separate component. So we did these, we have these thermal electrons and protons, which are Maxwellian, and then non-thermal pickup ions, we treat them as non-Maxwellian, so Maxwellian plus 2 order corrections. And we did that, and we calculated these equations for them. This is the continuity, momentum, and pressure equations. We have 2 pressure equations because pickup ions are not equilibrated with the background. So they have their own pressure, and since they are not Maxwellian, they have this dissipation term, heat flux and viscosity. But thermal gas was Maxwellian, so the right-hand side and the right-hand side is 0 and doesn't have any dissipation. So we use that, we did all the calculations. I don't go throughout the maths here, but this is the general shock structure equation that we can get. We can use this equation to solve any kind of shocks from parallel, perpendicular to oblique, and all this can be solved with this equation. So we use that, and we simulated the heliospheric termination shock. Okay, Voyager 1 and Voyager 2 cross termination shock, Voyager 1 at 94 AU in 2004, but it was during the data gap. So we don't have any data from that time. But Voyager 2 crossed at 84 AU in 2007, and we have data from that, and it was a surprise when we got the data. And from here is from Richardson et al. 2008. They have plotted the Mach number as a function of time. Here is the position of the termination shock. And you know that when we have a shock break, the flow should changes from supersonic to subsonic. So the downstream of the shock should have a Mach number less than 1. But when they plotted that, they saw that the Mach number is still greater than 1. It means that the flow is supersonic. So the energy is not going to thermal gas. It should go to another particles. So what we did, we have included pickup ions in the system, and we can see that we have plotted the combined Mach number. Here is changing from supersonic to subsonic. So the energy is going to pickup ions. Here are just some of the results. For example, here I plotted the inverse compression ratio, the compression ratio that we got comparing to the observed one. And also I have plotted the pickup ion pressure at the downstream of the shock is 1.57 times 10 to the 7 Kelvin. So we don't have Voyager observation. So we cannot see what is the temperature of pickup ion at the downstream of the shell. But it was a theoretical model by Zhang et al. 2010, and they calculated the pickup ion temperature should be in this range of energy, this range. So we have learned a lot about the heliospheric termination shock with Voyager, but they were not instrumented to study to have the pickup ions also. Also, we cannot see what is the energy partitioning across the termination shock. We don't know how much of the energy is going to thermal gas, how much is going to pickup ion, galactic cosmic ray, anomalous cosmic ray. So if we have a spacecraft that can measure all this range of energy and can also measure the magnetic field, so we'll be able to see what is the energy for each of these particles. Also, if we have a spacecraft that can measure pickup ions, we will be able to see how pickup ions are burning and how they are evolving when they are going through the heliosphere. The next region is inner heliosheath, and I want to study this medium. Here is Voyager 2 observation from Decker et al. 2015. They have plotted the pressure as a function of time or distance. And here is the termination shock crossing, and here is the heliopause. So this is inner heliosheath. The blue dots are the thermal gas pressure. Red dots are magnetic pressure, and the black are the energetic particle pressure in this range of energy, 28 keV to 3.5 MeV. And pickup ions have the energy of about just a few keV, so they are not in this range. And you can see that even though they are not measuring pickup ions, but the energetic particle pressure is the dominant pressure in the inner heliosheath. And then they have plotted the plasma beta as a function of time. And if you don't include any energetic particle, you see that the plasma beta is about 1. But if you include the pickup, the energetic particles, you see that the plasma beta is much greater than 1. So assume that when you add pickup ions, it will go much higher. So let me talk about this charge exchange again. So we have these energetic fast ions colliding with the slow neutral. So the energetic ion becomes the fast energetic neutral atom, and it can move in any any direction, and some of them can come to the Earth and can be detected by IBEX at 1 AU. There are some models that study pickup ions and energetic neutral atom. And for all of these models, there is a discrepancy between their model results and the IBEX ENA observation. So it should be some kind of energization of pickup ions in the inner heliosheath that we are missing. We saw that none of these models included shocks in the inner heliosheath. But we know that when the shocks propagate from the sun, they propagate into the heliosphere, they collide with termination shock, and then there will be lots of shocks in the inner heliosheath. And so we should include them in the model. So we included them, and we look at the Voyager 1 direction and calculated the ENA flux at 1 AU. Here is the flux as a function of energy. You can see they are IBEX high observations, and the average of first 5 years. And if these are the results of the previous model without including shock, so you can see this discrepancy between previous models and the IBEX observation. We assume that we have 2 shocks in the inner heliosheath. If we have 2 weak shocks, we got this ENA flux. If we have 2 strong ones, I got this red one. If I have 1 strong and 1 weak shock, we get this ENA flux, which is very closer to the observation comparing to previous models. So we can say that the difference between IBEX observation and previous models can be explained by considering the energization of pickup ions by shock wave in the inner heliosheath. So the question is that we don't know the number of shocks in the inner Helios sheet, and we don't know if they are weak shocks, strong shocks, how many of them are there. And also when the shocks are propagating in the inner Helios sheet and they collide with the heliopause, some get reflected back, some part of that gets reflected back, and some get transmitted into the interstellar medium. So in the inner Helios sheet, we have many shocks going in this direction and many reflected shocks. So it's a very complicated medium, and we don't know a lot about this. So we have to study that. And also we don't know, since we didn't measure the pickup ions in this medium, we don't know how the inner Helios sheet shocks are mediated by pickup ions. The next, I want to talk about the very local interstellar medium. And Voyager 1 and Voyager 2 are in the interstellar medium, and both still are measuring the turbulence of from the heliosphere in the interstellar medium. It means that the interstellar medium is affected by our heliosphere. Here, this plot is showing the electron plasma oscillation by Voyager 1 plasma wave instrument as a function of time. And you can see that sometimes we see an increase in the plasma wave oscillations, and some of them are associated with shock wave. And let me explain this as well. And this is magnetic field magnitude as a function of time. So here is the heliopause, similar to this. So we have seen two shocks in the inner Helios sheet by Voyager 1, in the interstellar medium by Voyager 1, and two pressure waves so far. So when we have an increase in the plasma oscillations, we can say that they are related to shock wave, and sometimes we see some increase in the plasma oscillation, but we don't see anything. And we believe that they are related to some shocks that are in distance, and they are connected to this. And so the shocks that were observed at the 2012 was very interesting, and it took 8.7 days for Voyager 1 to pass it, and that was a surprise because it was 10 to the 4 times broader than similar shock with similar properties at 1 AU, and there was no theoretical explanation for this kind of broad shock. So we used our model, and we simulated the very local interstellar medium. We assumed that we have supra-thermal pickup ions that are not equilibrated with the background. And so when we have pickup ions, so we have this dissipation term associated with that, viscosity and heat flux. Excuse me. Sorry. And we know that the heliosphere is collisionless. And we are interested to see if the very local interstellar medium is still a collisionless medium or collisional. So what we did, we calculated the collisional time scale and collisional mean free path for electron, proton, proton, electron, electron, and proton, protons. And we calculated the diffusion length, the collisional mean free path. And we saw that these numbers are small. It means that the very local interstellar medium is collisional. And unlike the heliosphere, which is collisionless. So when we have this, when we have collisions, so we make some dissipation in the system. We have dissipation, so I calculated the dissipations that we get from collisions and compare with the dissipation that you can get from the pickup ions, and I compared that, and we saw that this is much larger. So it means that we have to include these dissipations associated with collisions. And I simulated the 2012 very local interstellar medium shock, and this is just the results of that. You can see here we have inverse compression ratio that we get compared to the observed one. So this is a smooth and shock transition. And then I plotted the magnetic field, and you can see that this is, interestingly, the thickness that we get is similar to the observed one. And it was 8.7 days. Then I plotted the magnetic pressure in in green, and this is thermal gas pressure and then pickup ion pressure. You see that the pickup ion pressure is very small, so this shock is not mediated by pickup ion. So the thickness that we are getting here corresponds to the thermal heat conduction length scale, and the shock is determined by the proton-proton collisions, and it is controlled by the particle collision, not the wave-particle interactions, because the heliospheric shocks are controlled by the wave-particle interactions. So this medium is completely different medium. So when we are going from the inner helios sheet, which is a collisionless dominated by pickup ions, when we go to the inner interstellar medium, is a collisional and not mediated by pickup ions. So this transition is very interesting, and we don't know a lot about this. So instead of summary, I wanna list some of the open questions that we have about shocks and in general about the very local interstellar medium. Some of them are, how does the strength, thickness, and the speed of very local interstellar medium shocks change with distance from the heliopause? And actually how many of shocks can get into the interstellar medium? And what are the properties of the heliospheric shock that survive and reach the local interstellar medium? What is the origin of the pressure wave? Because you could see that I showed in this one, we have two pressure waves here, and we don't know what is the origin of these pressure waves. So we should solve that. And the other question is, what is the role of the collisionality in this medium, and what scale is the interstellar medium is collisional? And when do collisionless wave particle effects become important or even dominant? What are the properties of pickup ion in local interstellar medium? And so since they have some kind of different origins, each of them should have maybe different properties. How far from the heliopause are energetic pickup ion found in the local interstellar medium? And how far does the local interstellar medium mediated by heliosphere? And when we are going to go to the pristine interstellar medium? And is there any bow shock or bow wave in front of the heliopause? And I can go to many more questions, but I'm gonna stop here. And so these are the questions that were raised by Voyager 1 and Voyager 2. And so since they were not instrumented to study the interstellar medium, we were not able to answer this question. So we need another spacecraft dedicated to study this medium. And the next speaker, Elena, is gonna solve our questions and our problem.
It's a wonderful talk. We're going to switch to Elena. Just one comment, Parisa. I think New Horizons will arrive to the termination shock. It seems that there will be enough, at least what I was talking to Alan Stern the other day, that there is enough energy to push it to 100 a year.
So this is something new, because since the last year I talked with Dave McComas, he said that it will not reach the helium.
I think it,
we have plenty of fuel and to get to the termination.
Okay, that's a good news.
That's a good thing. It seemed like
the heliopause maybe not, but the
termination shock, I think so. Yeah, I think it will.
Okay,
so keep your questions for Parisa. Write in the chat if you want. I have some, but I will leave it for later. Okay, Elena, the floor is yours.
Thank you, Mirav. So let me share.
Hopefully you will be able to share your video.
I hope so, yes.
Okay.
So you're seeing empty screen, right?
Right.
Now you're seeing my slide, right? Do you see my slide?
Yes.
Okay, fantastic. So, Mirav asked me to spend some time on my story. So, well, first of all, thank you very much, Mirav, for inviting me to talk at this SHIELD webinar. It's a pleasure to speak in a SHIELD webinar. And Yeah, so let me tell you who I am and why I'm here. So I joined Moscow group, who is well known for development of global models of the heliosphere when I was undergraduate student. And I started working with Dr. Vladis Modenov. And my undergraduate project was numerical modeling in hydrodynamic approximation of the interaction between interstellar cloud and the hot plasma, so the intercloud material. And let me tell you one story about the moment when I really decided to work in heliosphere science. So when I was an undergraduate student, Vlad invited me to participate at the meeting in Bern, in EC. And the meeting was called From the Outer Heliosphere to the Local Bubble. And Mirav, this is the first time I met you.
And you were shocked forever.
So 13 years ago, that was October 2007. And you see that photo here in the bottom on the left. It's some from left to right. It's Dimitra Kurtumpra. She's from Latmos in France. And then Vladis Modenov and Vladimir Boranov and myself on the right. So that was October 2007. And at this meeting, John Richardson presented this breaking news from Voyager 2 that the spacecraft just crossed the termination shock a month ago at the distance 84 astronomical units from the sun. So, and before that, in 2004, Voyager 1 crossed termination shock at 94 AU. And I cannot express in words how I was impressed seeing that data, because before that, I read this classical paper by Baranov and Malaman 1993, where they predicted the similar distance to the termination shock from their self-consistent model. And I just could not believe that moment, you know. And it was also striking that that crossing of the termination shock happened 10 AU closer to the sun. And I remember I could really feel how the scientists in the room started thinking about why the termination shock is asymmetric. What are those effects that result in this asymmetry? Is it interstellar magnetic field, or is it the time-dependent effects? And that was really one of the moments when you fell in love in science and you have confidence that this is what you want to do, and this is where you want to pursue your career. So later I joined Mirav's group in 2010, and we worked on simulations of the time-dependent heliosphere. We considered several problems and performed simulations to understand how shocks in a heliosphere driven by, let's say, coronal mass ejections, how those shocks transmit through the heliosheath, how they interact with the termination shock, propagate through the heliosheath, and then interact with the heliopause. And we also looked at the global response of the heliosphere to the changing solar wind with time and latitude. And I had my defense in Space Research Institute in Moscow, and Mirav really wanted to be there, but we realized that the defense could only be in Russian.
I know, and I couldn't learn Russian fast enough.
Yes. So I spent a great few years with the U group, and you can see them on this picture on the bottom on the right. So after doing a couple of postdocs, I found my home at APL, and on this slide, I'm just summarizing what I do now. So for my research, I work on simulations of the solar wind and semi-propagation in the inner heliosphere from sun to Earth. I use Gamera code, which is newly developed MHD code. And one of my current projects is to perform a large number of CME simulations from propagating from sun to Earth. And here we're talking about 50,000 simulations, and that's for the statistical study toward development probabilistic forecast methods. And I recently joined Punch science team to work together on development, modeling, and data analysis tools for the mission. So I'm also part of the team at APL that lead the concept study for the Interstellar Probe mission, and I will talk more about this in my next slides. And I'm also the Deputy PI for the SEALA mission. So SEALA is the heliophysics mission of opportunity to investigate the heliosphere boundary and determine the latitudinal structure of the solar wind through observations of solar Lyman alpha emission backscattered from interplanetary hydrogen. And SEALA is in phase B study right now, phase B mission phase. So, and we talked with Mirav, what should I talk today? And we decided that since Interstellar Probe mission concept is mostly closely related to the SHIELD science, so I'm gonna talk about the Interstellar Probe. And I apologize if I repeat a lot what we said just a couple days ago, presenting webinar with Pontus, who is a project scientist for this study. So Interstellar Probe, a future mission to unravel mysteries of the heliosphere and its interstellar neighborhood. So what is Interstellar Probe? So since the beginning of the space age, people dreamed of going to another star, and since 1960s, scientists have discussed about going beyond our heliosphere, beyond the boundary of our bubble to the unexplored interstellar space. And of course, we're not going to another star, but Interstellar Probe is the first step into the local interstellar medium, local galaxy. Interstellar Probe will travel through the heliosphere boundary into the very local interstellar medium to at least 400 astronomical units from the sun. So we're not a starship. Interstellar Probe will be a large strategic mission that uses available technologies to achieve asymptotic speeds by a factor of 2 to 3 greater than those of Voyager 1 and 2 spacecraft. Of course, Voyager 1 and 2 were the first who discovered the heliosphere boundary and explored the very local region near our heliosphere from outside. And the science, of course, the science questions have been with us over decades, and it's completely enabled to go into this new unexplored space, the local interstellar medium. There are also opportunities on this mission for planetary and astrophysics, and I'll talk a little bit more about this. So also, lastly, the Interstellar Probe also paves the way for next steps on longer journeys, future journeys beyond in many different ways, scientifically, technically, and programmatically, of course. So now let me see if the movie starts. Does it play?
Yes.
Yeah, okay. So
Yes,
during
Elena,
its,
yeah.
maybe let me then start again. And yeah, so during its evolution, our sun with the heliosphere completed 18 revolutions around the galaxy. And, during its journey, the sun plowed through very different interstellar environments that, of course, shaped the system that we live in today. And the orders of magnitude differences in properties of interstellar plasma and gas are responsible for the extreme range of sizes and shape of the global heliosphere throughout its history, its journey in the galaxy. This also has consequences for the penetration of the interstellar material that have made all of us and that have affected several crucial aspects of elemental and isotopic abundances and conditions for habitability in the solar system. So in about 1500 years, the sun will likely enter a new environment, different interstellar environment, and perhaps will go through some other transition, and it will affect its shape and global structure. So Interstellar Probe is the pragmatic mission concept that would explore the heliosphere boundary and the unknown gas, unknown environment of the local interstellar cloud where sun propagates. So the mission is designed for a lifetime of 50 years and enabled by Jupiter gravity assist to get to about 400 astronomical units from the sun. And this is more than twice the distance of Voyager will ever reach. So in a sense, Interstellar Probe will investigate that snapshot in time of our sun's journey through the galaxy to understand the physical processes that operate in the heliosphere and how solar wind interacts with the interstellar medium, and inform us how our bubble, where it came from, and where we're going. So let me talk about the heliophysics science for this mission. So we have, this is the primary goal for the mission, to understand our inhabited astrosphere and its home in the galaxy. And there are three science objectives for this goal. The first objective is to determine the physical processes that shape our heliosphere. So here we're talking about this global shape and structure and processes that create it. And for objective 2, to determine how the sun's activity in the interstellar medium and possible changing properties in the interstellar medium, how they influence dynamics and evolution of the global heliosphere. And for objective 3, discover and quantify directly the unknown properties of the very local interstellar medium. So for the objective 1, of course, we talked about the global shape, the shape of the heliosphere, where it has a comet-like shape, or it's more like a bubble or croissant shape or something else. That's one of the biggest questions in the community. And we have data from IBEX and Cassini in ENAs in different energy ranges. And these data suggest different shapes. So IBEX data was interpreted that the heliosphere has a long tail, and Cassini data suggests that heliosphere is more like a bubble confined by the strong interstellar magnetic field. The models also do not agree about the shape. And here in the middle, you see the simulation that shows how heliosphere might look like as we see it on Interstellar Probe in energetic neutral atom fluxes at the distance 250 astronomical units from the sun. Let me track time. So also Voyager's encountered completely new plasma regime in a heliosheath, as Parisa already described in details, where plasma is dominated by, but pressure is dominated by particles with energies larger than thermal, so-called pickup ions with energies of few keV. And Voyagers did not measure pickup ions, leaving us with the gap in understanding this crucial particle population and their role in upholding our heliosphere. So measurements of particle distributions in a large energy range from thermal through superthermal to high energies will enable to determine energy partitioning and pressures across the termination shock heliopods and heliosheath, of course. The next slide. So the termination shock transition was indeed the first signature of the heliosphere edge, and this is the largest shock in the heliosphere, and we expect it to be the strongest. But the observed plasma, observed changes in plasma fields and energetic particles at the shock transition were completely unexpected. So the shock heated plasma very little, and the plasma flow stayed supersonic in the heliosheath. That was quite a surprise. And it's important to revisit this region with measurements of ions up to 100 MeV per nucleon, with measurements of electrons and fields and waves with high cadence, to discover the acceleration processes and energy balance and turbulence and electrons' behavior and properties. Another big question is the mechanism that create anomalous cosmic rays. So anomalous cosmic rays were discovered by Voyagers, and the expectation was that this is a termination shock that acts as efficient accelerator. So anomalous cosmic rays are particles that start as interstellar neutrals. They get ionized and accelerated to tens of MeVs in energies. However, what we saw is that termination shock did accelerate particles, but not to the higher energies that was observed. And intensities of anomalous cosmic rays continue to raise as Voyagers traversed into the heliosheath. And with measurements of particle distributions and fields on Interstellar Probe, we will be able to distinguish between existing different theories how anomalous cosmic rays are created, where they're created in the tails of in the flanks of the Helios sheath, or by turbulence reconnection, or by something else. So another mystery, of course, is the heliopause. Voyagers discovered that it's not the plane surface as we envisioned it. There are some complex instabilities taking place, and complex interaction between solar particles and interstellar particles at this boundary. And also the magnetic draping. It came a complete surprise when Voyagers exit the heliosphere. They measured the magnetic field direction, and we expected that the direction of the magnetic field would be sort of north-south compared to east-west direction inside the heliosphere. But the complete surprise was the direction of the magnetic field outside the heliosphere in the interstellar medium is the same as inside the heliosphere. And you can see the simulation that Mirav did, showing this magnetic draping. So we still do not understand how the magnetic fields of different origin interact with each other to create this draping. So now let me move to the second objective. I need to speed up a little bit here. Of course, yeah, the second objective is the variable sun in a changing interstellar environment. The heliosphere is very dynamic, and it changes through the solar cycle, as you can see in these maps on the left from IBEX High, how this global interaction shown in fluxes of VNAs, how it changes in terms of structures and intensities during the solar cycle. And as Interstellar Probe will leave the heliosphere, it will image the global heliosphere evolution under very different solar conditions that we saw in the past and in the next solar cycles. Also, Parisa talked already about the shocks. One of the very interesting questions, how far does the influence of the sun extend into the interstellar medium? How far those shocks can propagate in the interstellar medium? But it's not only the sun that controls dynamics, but also the interstellar medium. And there could be regions with different densities of hydrogen in the interstellar medium, and different levels of ionization, of course, different temperatures. And here on the bottom, I took these simulations from Müller et al. 2008 to show you that you can see if the sun is going through the dense interstellar cloud with high density of hydrogen atoms, you can see how small the heliosphere can be, that the distance from the sun to the heliopause would be 25 AU. And remember that Pluto is about 40 astronomical units. So Pluto would be outside of the heliosphere. And a simulation on the right shows the opposite case, when sun is going through the tenuous and very hot plasma in the interstellar medium, when heliosphere is getting inflated, and heliopause distance would be 300 astronomical units from the sun. So so now the third objective is to discover and quantify directly the properties of the unexplored local interstellar medium, the properties such as neutral gas and plasma density and temperature and composition and dust properties and particle distributions and turbulence and magnetic field. We don't know these properties. We never measured them. So the local interstellar medium is a completely new area for the discovery. We know very little about it. So from line of sight spectra toward different stars, we only have this global view in scales of light years. And there are studies that suggest that the sun could be in contact with 4 different clouds, and it's not clear what would be the next destination of the sun in the interstellar medium. But the ground truth about the properties of the very local interstellar medium is missing. We only have a sparse understanding inferred from in situ measurements inside the heliosphere of interstellar helium, measurements of pickup ions and ENAs, and backscattered Lyman alpha emission. So the first step into this unexplored region of space would offer the first sampling of particles, fields, and dust that hold the key in understanding the heliospheric interaction, the interstellar environment, and chemical evolution of the galaxy. So once we exit the heliosphere, the first interesting feature is the hydrogen wall. So the hydrogen wall, it's a region around our heliosphere with hotter and slower hydrogen atoms. And the hydrogen wall forms because of the charge exchange process between interstellar hydrogen coming into the heliosphere and the interstellar plasma that slows down around the heliosphere. So the hydrogen wall was predicted by global models and was discovered as excess in absorption in Lyman alpha spectra towards stars. And similar absorption was detected in other astrospheres, meaning that this is the generic astroperic phenomena. And it's not just hydrogen wall, it's also oxygen wall and neon wall. So we don't really know the composition of this feature. And it was never observed in situ. Also, Parisa talked about the bow shock. We don't know the nature, if the bow shock exists in the interstellar medium or what's its nature. Also the dust, and Virli is on the line and she's expert in the interstellar dust. We have very little knowledge about how dust interacts with the heliosphere. We just started looking at the global models with interstellar dust and how dust propagates into the heliosphere, how it interacts with interstellar medium. And also Interstellar Probe opens unique opportunities for new science in galactic cosmic rays. And the completely unexplored part of the galactic cosmic ray spectrum is below 1 GeV. So above these energies, galactic cosmic rays they don't fill the heliosphere, they just propagate inside, and we can measure them at Earth. But below these energies, they're shielded by the heliosphere. So the only way to understand the origin of the cosmic rays, of these cosmic rays and these energies are going outside the heliosphere. And of course, the measurements of elemental and isotopic abundances of the galactic cosmic rays enable to distinguish between different sources and look at the elemental fractionation and the spallation processes in the interstellar medium. So there are other unique opportunities for planetary science and astrophysics, and this includes the flybys of the dwarf planet or Kuiper belt object. Also the imaging of the dust disk around our sun, and measurements of the extragalactic background spectrum. And I would not go into much details because of the time. And so now let me just tell you why I am excited about this mission. To me, this is really one of the kind mission, and this is mission to understand our home in the galaxy. You can place your bets on what is the heliosphere shape, what Interstellar Probe will see. This is, of course, going to be the furthest spacecraft ever sent, and we're going to a new place, and we don't know what we're going to find. So discoveries evade, and we may not be even smart enough to ask the right science questions for this mission, because nature is always going to be smarter. And just like Parker Solar Probe went to the region where we've never been before and discovered something that we not even expected. We did not have this science question for the mission, and Parker Solar Probe discovered this switchbacks, and now we're trying to understand what it is, what it means, and what's the origin. Another example is that, for example, our view on planetary systems around other stars have revolutionized when exoplanets were discovered. So I'm sure that Interstellar Probe will enable discoveries of the processes and physical mechanisms that control this interaction of a star with its galactic surrounding. And there will be a lot of discoveries. Also, the 50 years of lifetime of the mission. It's challenging. It's hard to imagine. For example, I'm thinking that Python that we all use today in our science, it will not even exist when our kids look at the science data from Interstellar Probe. And another aspect is the handoff of the knowledge, and it's already happening, and it's extraordinary opportunity to work with amazing people. And I would also like to call Parisa and ask her if she could also share why. I know she is excited about the Interstellar Probe mission. If you could, Parisa, also share your excitement.
Sure, thank you so much. First, thanks for the talk. And actually, you mentioned all these reasons that I can be excited, but other thing, because Interstellar Probe is it's gonna go very far, and it's going to be the first human-made spacecraft with dedicated instrument to study outer heliosphere and interstellar medium. It will be the first to go to pristine interstellar medium, and it will be first to picture our own home, and many, many more firsts. And there is lots of exciting science that we will learn during this mission, and in general, it can answer all the questions that I mentioned in my talk. And it will make new ones for us to think about them. And most importantly, I'm excited to be part of this team and to work on this mission and to make this mission reality. And you mentioned that Interstellar Probe is not a new idea. It was around since 1960s, but the problem was we didn't have equipment, and I mean the technology to do that. But right now we have the technology, so it's time to do that, and we don't have any more excuse, and we should do that, and we should go to the Interstellar Probe and learn about this medium.
Thank you very much, Parisa. And I think this is the probably great point to conclude this presentation.
Thank you so much, Elena and Parisa. Was wonderful. Can I just make a comment that, you know, when I got into the field, and it was many years ago, I'm not that young, but I was one of the youngest in this community. So it's so nice throughout the decades to see, at least almost 20 years I'm in the field, how younger blood came in and the field being transformed slowly. It started a lot with Voyager that had an older population because it came from the beginning of the mission. And then with IBEX, now with IMAP, with Interstellar Probe. So it's an influx of younger, and I'm so excited to see what will happen with Interstellar Probe passing the baton. You guys will be the one to run those missions. We are almost to the top of the hour. Maybe we can extend by a couple of minutes. There is so many questions in the chat. I have as well questions. Verle is saying, still using IDL. Yes, IDL to the Interstellar Probe. Yeah, photon. No. Anyway, there was some question from Drew. I think one of the first one. Drew, you want to do it?
Yeah,
I think.
sure.
Yes,
Thanks,
sure.
Mirav.
Mm-hmm.
So this one was for Parisa. I was wondering, and I'm completely a noob to this whole community. I'm trying to learn as quickly as I can, and I love it. I'm really excited about everything that everyone's researching, as well as Interstellar Probe for sure. So Parisa, I was wondering, is there any one-to-one correspondence between known solar wind transients, and by that I mean, like, say, coronal mass ejections that we observe coming off the sun, and those shocks that Voyager's observing in the very local interstellar medium? I'm wondering that, considering the long transit times for the solar wind to propagate out to the outer heliosphere and into the local interstellar medium, and the difference between the velocity of these CMEs, I'm assuming that there's some coalescence of those before they get to, or some bunching up of those before they get to the boundary. And considering that, do we have any idea of how many of them have bunched up before they're observed out there by Voyager?
Yeah, thanks for great question. And there are some models that they have studied the propagation of shocks from the sun to the outer heliosphere, like Washimi et al. 2011. They studied the propagation of shock during solar cycle, and also our own Elena has a research about that. She also looked at that, and maybe she can add also. And yeah, you're right. When the shocks are propagating, they can merge, they evolve during the time, and their compression ratio, everything is gonna change during the time is going, and they merge a lot. So maybe 10 shocks becomes, I don't know, I'm just guessing, 2 shocks when they get to the inner heliosheath. And this is regarding to the models that we have. And about the Voyager observation, when I talked to Lemberlaga, he believed that because of the inner heliosheath is very turbulent medium, they were not able to see a clear shock in the inner heliosheath by Voyager. So maybe because the instruments were not good enough to look at the turbulence over there and separate the turbulence from the real shock over there. So that's another reason that we need Interstellar Probe to go there and detect all the shocks over there for us.
I can just make a quick comment that working in Voyager for so many years, it was every 6 months a new surprise. So there's nothing like an in situ mission that it's go there and it's completely throw out of the window all your ideas. So it's the best. So for theoreticians, for modelers, for observers, it's nothing like you expect. So nature, it has enormous surprises. So I'm sure we will say Interstellar Probe and we'll have to revisit. Yes.
Merav, you're speaking my language. I'm an observational scientist, so you're
exactly.
totally.
This is it. Yeah, nature is way cleverer than all of us. Folks, we are reaching the top of the hour. Maybe we'll do one last question. I got a question from Verly about the extent of the nose direction. I can tell you from modeling, it's depend of 300 AU, depends where you're looking.
Is that the hydrogen wall?
What?
Is that the distance to the hydrogen wall?
Well, the hydrogen wall is in between the bow shock and the nose.
Okay.
The extent of it.
Mm-hmm.
So it's go to 300 to 400. It really depends. And if you don't have a bow shock, it's slow bow shock, but it's more or less a distance. Okay, folks, thank you so much for attending. We hope to do more of that, these young voices. I've been wanting to do that for a long time. So we hear the younger folks talking. They're way more excited and way more interesting stuff that they're doing. I would love to have more of you guys reach out to us to give more talks. Thank you so much, folks. See you next month. Bye.
Thank you, Merav.
Thank you, both of you. And we will be posting this on the web.
All right.
Okay. Bye, folks.